Okay, so I want to record a little bit because a few people aren't here today and might, want to know how we're doing these logarithms. So in the past, you have learned about exponents, such as 2 to what power would give you 32. Well, now we're learning about logarithms, which are inverses of exponents. So if they change an exponent into a logarithm, they just write it differently. The base number is 2. They make that number small and put it down next to the logarithm word, like down in the corner. So they put log base 2, and then they put the answer of 32, and you're supposed to figure out what the exponent is. So they just write it in a different order. See, it's log base 2 of the 32 equals x. But it's asking the same thing, log of what? Or like it's asking the same thing, like what's the exponent? 2 to what power gives you 32? So when I see a logarithm, most of the time I just think of the exponent version. And I rewrite it back as an exponent, and then I try to think what would give me that answer. 2 to what power would give me 32? And you can take that big number 32 and break it apart and see, divide it by 2, which is 16, divide that by 2 again, 8, 2 times 4 is 8, 2 times 2 is 4, and you can see it breaks down into 5 2's. 2 to the 5th power then would give you 32. So the answer to this logarithm, log base 2 of 32, it'd be 5. The answer is 5. See, it's the same as thinking of it as an exponent. So here's another one just to kind of look at really quick. This one is log base 4 of 64. So again, you're thinking 4 to what power would give you 64? 4 to what power would give you 64? So you can take 64 and divide it by 4. I just use like a tree, factor tree. And 4 times 16 is 64. Then 16 is 4 times 4. And I see 3 4's there. So my answer is 3. 4 to the 3rd power gives me 64. See, log base 4 of 64, it'd be 3. All right, so hopefully you'll kind of get the idea that a logarithm, you can just rewrite it back as an exponent again and figure out the answer. Okay, a few that always come up that are kind of tricky for people to remember, or it's just one you just have to remember because it's a property you learned when you were younger in Algebra 1. Like if it says log base 3 of 1, well, what is that? You're thinking 3 to what power would give you 1? And sometimes it's hard for people to think of that. How is this going to work? It's just a property, like you were taught it in Algebra 1, that anything to the 0 power equals 1. So the answer is 0. So you'll have to try to remember that one. Anything to the 0 power would give you 1. If it says what's log base, any base would, like if it was just log base 5 of 1, it'd be 0. Log base 10 of 1, that'd be 0. Log base e of 1 would be 0. So any log of 1 is 0. So you can kind of make a note of that because that's an important one that keeps coming up. And then there's a thing called a common logarithm. It's just like common because it's used a lot. A lot of times people think of numbers in base 10. The common logarithm is a base 10. So if they said log base 10, that one's considered the common logarithm. And that logarithm is a key on a calculator. Like my standard calculator here, my TI-30, the log key, that is a log base 10 key. It doesn't have a place, it doesn't have like a little base number down by the log word. It's assumed this one's log base 10. This one's the common log. And you can solve log base 10 questions on a calculator. But if it's not log base 10, like these up here that I showed you, you have to think through them. Like 2 to what power gives me this? But yeah, common logarithms are log base 10. So if I asked you, what's log of 1 over 100? The 10, the small letter 10, number 10, they don't always put that there is what I'm saying. If they don't have a little number there, everyone knows it's log base 10. So if they ask you what's log of 1 over 100, It's asking 10 to what power would give you 1 over 100. See, they would write it just log parentheses 1 over 100 and ask you to figure it out. And like I said, you could use a calculator to do that. It's asking 10 to what power gives you 1 over 100. And the answer comes out to -2, because we know 10 squared is 100, but you need that negative exponent makes it into a fraction. And you can, like I said, you can do it on the calculator, log of 1 over 100. If I just type it in, since it's a common log, I can do it on my calculator. See, it gives me -2. And then there's a natural logarithm, which is base e. E is a number, 2.718, keeps going. It's a number like pi. It's an irrational number. There is a key on the calculator that shows you e to the first power. So e is 2.7182818. And so it's just a number like pi that you've studied before. And if you're working on log base e, they call it a natural logarithm. And again, there's a key on the calculator for this. So natural log is log base e. And they don't put the e there. It's like, it's assumed. Everyone knows when you write ln, everyone knows it's natural log base e. So they would just ask you something like, what's natural log of 5? And you could grab your calculator. It means like e to what power gives you 5. And you can just grab your calculator, type it in. Natural log of 5 is about 1.6. All right. Then we're getting to the end here. I just wanted to record a few things because, you know, for people, if they're absent, they can watch the video. There's a one-to-one property where if you have logarithm base 4 of something on one side of the problem and logarithm base 4 or something else on the other side of the problem, if you have the same logarithm with the same base, then you can just equal these arguments. It's called a one-to-one property. Like, these should be equal. If you have log base 4 on both sides, then these should come out equal. So then you would just easily solve it. 2x plus 1 equals 3x. I would subtract 2x and I would get x equals 1. So you'll apply that a few times on your assignment, this one-to-one property. Here's another one I wrote. Log base 10 of, well, it didn't even say base 10. It just says log of x squared minus 6 equals log of 10. And I wrote that in red just to highlight. See, if it just says log, it is log base 10. It's natural log, or common log. And if it says log base 10 on both sides, you can just get rid of that and equal your arguments. X squared minus 6, you could equal that to 10 and solve it. You could add 6, so x squared equals 16. Then you take the square root of 16, you get plus and minus 4. Don't forget when you take square roots, you have to do plus and minus. And then finally, maybe back to one more graphing one to review. So earlier in class, we were talking about the exponential functions and their graphs. So if they asked you to graph a logarithmic function that said log base 2 of x minus 4. Well, again, the logarithmic functions and the exponential functions, they're inverses of each other. So you could, to help you, you could think about it being similar to the graph 2 to the x minus 4 power, the base 2 to this power. So this graph 2 to the x minus 4 power, if I asked you which way that graph moved, did it go to the left, right, up, down, which way was it transformations? When they add the number up in the exponent, that moves the graph. It moves it, and if you think about it which way, moves it 4, and we talked about it last time. We hadn't, if it's in the exponent, it moves it left or right, and it's opposite of what you think. If it says minus 4, it actually goes like positive 4 to the right. So if you think that of your exponential function, and we've graphed them earlier in class, this moves it 4 to the right. 1, 2, 3, 4. So the logarithmic graph would move 4 to the right. And that's important to pay attention to. It moves it 4 to the right. It actually affects the vertical asymptote of the graph. It would be, instead of at x equals 0, instead of being at the center of the graph now, because the logarithmic graphs usually are right, if it's not shifted left or right, they are right here, right along, they have a vertical asymptote usually of x equals 0, right along the y-axis. But if we're moving 4 to the right, now your vertical asymptote is x equals 4. So if I go 4 to the right, 1, 2, 3, 4, make a dotted line there for your vertical asymptote. That's going to be really helpful. It shifts your domain of the graph too. Your domain would be x greater than 4. Or your graph, you could say, goes from 4 to infinity, if we want to write it in the set builder notation. So your logarithmic function would end up over here. Like your exponential function, I could graph that. It would go here, kind of like this. You could sit and make a table and plug in numbers to graph your exponential function. And then your logarithmic function, like I said, moves 4 to the right, and it ends up down kind of in this region. And if you want specific points, you'd have to sit and make a table. You have to sit and make a table if you want specific, if you want to get real. I just sketched it really quick just now, but if you want to get the points, you'd have to pick numbers greater than 4, like 5 or 6, and plug them in. If I go back to my log function up here and plug in 5, it would say log base 2, and then I'd plug in 5. 5 minus 4 is 1. And I'd have to figure out what log base 2 of 1 is. Whenever it's a log of 1, that always equals 0. So 5 comma 0, 1, 2, 3, 4, 5. Like, I knew it was going to hit there because I've done these enough times. I sketched it for you. See, it's that is an actual point right there at 5 comma 0. And if I plug in 6 into there, 6 minus 4 is 2. It would say log base 2 of 2. That equals 1. 6 comma 1 would be right here. See, and I just sketched it really quick for you, so I wasn't being like super specific on my points, but I basically had them in there. But yeah, if you want to get it real specific, you have to sit and make your table. Same with this one. If you were going to be real exact and precise, I literally just sketched it for you really fast, but I could sit here and plug in numbers and make a table. Again, if I plug in, I'd think of what numbers I want to plug in here. Like, I'd probably plug in, since I went 4 to the right, I'd probably plug in 4. 4 minus 4 is 0. 2 to the 0, that'd make it 2 to the 4 minus 4 power, see? And that'd be the same as 2 to the 0. Anything to the 0 power equals 1. So 4 comma 1. 1, 2, 3, 4, 1. Yep, and I have that point right there. If I plugged in 5, 5 minus 4 is 1. 2 to the 1. 2 to the first power, that's 2. So I have 5 comma 2. See, and I basically sketched those for you already. I was just graphing it real quickly. So hopefully that helps as you work on your assignment. I wanted to make a quick video because I knew a few people weren't here today or had to check out early for an appointment. So yep, so I'll post this on Canvas and let us know if you have any other questions. Always, you can email me or send me a question